This video is on topic 1.6, photoelectron spectroscopy. Today we're going to cover how to read a PES spectra to determine the identity of an element, the electron configuration, and predict the relative energies of the electrons. My name is Alice Pudi, and I'm happy to be back with you on AP Daily. When we think of the atom, we think of electrons as existing in shells and subshells or energy levels and sublevels, where the inner electrons are the core electrons and the outer electrons are valence electrons. So what you see here is a sample electron configuration where the 1 here would represent the shell or energy level and the P would represent the subshell or sublevel. But how do we know what order the electrons fill and how many electrons go in each level or sublevel? And so that brings us to Aufbau principle. The Aufbau means to build up, and it is German. And what it says is that electrons will fill lower energy levels first and then fill higher ones later. So if we start at the bottom of the model here, there would be 2 electrons in the 1s, then 2 electrons in the 2s, then 2p. And so we would go from the bottom to the top and then from left to right. But how do we know what this order is and how many electrons go in each spot? And so that brings us to photoelectron spectroscopy, which is also known as PES. And so what PES is a technique that's used to determine the relative energies of electrons in either atoms or ions. And this technique uses high energy radiation to remove an electron from an atom. We already know that electrons are located in different energy levels or subshells, and that valence electrons are easier to remove since they're less attracted to the nucleus, and core electrons are harder to remove because they're more attracted to the nucleus. All right, so let's take a look at an example of a PES. So this example of a spectra here, you can see on the x-axis we have the binding energy, which is measured in megajoules, and on the y-axis is the relative number of electrons. And so the placement on the x-axis indicates how much energy is required to remove that electron from a subshell, and the height of the peaks that you see here is proportional to the number of electrons that are in that subshell. Generally, when we read our PES, we think about the nucleus as being here on the far left, which means that this peak represents the electrons that are closest to the nucleus, and then this one would represent the electrons that are furthest away. When we analyze the peaks here, you should notice that these 3 peaks are the exact same size, which indicates that it's the same number of electrons. And then this larger peak here is about 3 times greater, which indicates there are 3 times as many electrons. So if we take a look at the electron configuration then, again, this peak represents the electrons that are closest to the nucleus. So this would be 1s, and there are 2 electrons there. Next comes 2s2, and again, same number of peaks, or same height of peak, which means same number of electrons, and then 2p6. And again, this one has 3 times as many electrons as this peak, and then the last one is going to be 3s2. From here then, we can identify what the element is one of 2 ways. We can either count the superscripts, so 2, 4, 10, 12, and element 12 is magnesium, or we could note that the configuration that ends in 3s2 is for magnesium. We can also use PES to compare different elements. So for example, we're going to take a look at beryllium and magnesium, which we just looked at, and tie this back to Coulomb's law, which was part of the last video. And so I've already filled in the electron configurations for both of our elements, and we're just going to look at the valence electrons in each of these cases. So you can see that for beryllium, its valence electron peak is at 0.90, and for magnesium, it's at 0.74. Indicating for magnesium that it takes less energy to remove the valence electron than it does for beryllium. So tying this back to Coulomb's law, remember again, if our R value is increasing, meaning the distance between the electrons and the nucleus is greater, that means the force of attraction is less, and that means that there would be less binding energy. This is the end of the video. Thank you for watching. Please join me for the next video where we take a look. This video is on topic 1.6, photoelectron spectroscopy, and today we're going to take a look at some PES practice questions. My name again is Alice Pudi, and I'm happy to be back with you on AP Daily. In the last video, we took a look at how to read a PES spectra, and so we're going to use that information to answer a question here. So again, right? We already talked about how to determine how many electrons there were and the placement of the electrons. And so what I'd like you to do is answer this question, which asks, based on the spectrum, write the ground state electron configuration of the element and identify the element. Press stop, answer the question, and then press play when you're ready to continue. When we look at this spectra, you should hopefully recognize that all 4 of these peaks are the same size. So that would indicate how many electrons that we have in each of those places. These 2 larger peaks are also the same size, indicating that we have the same number of electrons there as well. I think in general, even if a question doesn't ask you to identify the electron configuration, it's always nice to know what element that you're looking at in having to answer questions on. So even if the question didn't ask you to do this, I do recommend always that you write your configuration. I choose to write mine above the peaks here. And so in this case, we're going to go out to 4s2. And if we count all the superscripts here, or we just recognize what element ends in 4s2, then this should be calcium. Next, we're going to take a look at another example. For this example, then, this spectra you're going to use to answer these 3 questions. Before I have you answer the question, I just want to point out for part A that the question asks you to draw an X above the peak that corresponds to the orbital with electrons that are closest to the nucleus, and then to justify your answer in terms of Coulomb's law. So make sure you do both of those for part A, and then part B and part C. Press stop, answer the question, and then press play when you're ready to continue. Hopefully you put an X above the peak that was at 100 megajoules for its binding energy. And again, the question says to justify your answer in terms of Coulomb's law. So then I put a little summary of Coulomb's law that says that the attraction between charged particles increases as the distance between them decreases. And again, just stating Coulomb's law isn't enough. You need to take your answer and tie it back to Coulomb's law. So then the last thing that I described here was, since this peak has the highest binding energy, that means these electrons must be closest to the nucleus. What you can't say here in order to receive credit is that this is furthest to the left, which means that it must represent the closest to the nucleus, because that doesn't answer the question in terms of Coulomb's law. So you want to make sure that you're reading the question and answering what it's asking you for. For part B, if we write the configuration for this, then it should end in 3s1. And though it doesn't ask for it, this indicates that the element is sodium. And then the last thing says to draw a peak that corresponds to the valence electrons if the element had 1 more proton. So when you draw your peak, you want it to be further to the left, and that's because 1 more proton means that there'd be a stronger attraction between your protons and your electrons, and so it would take more energy to remove that. And then it also needs to be twice as tall. And the reason it needs to be twice as tall is originally the 3s1 peak has only 1 electron in it. And so if we add 1 more proton, that means that I also need to add 1 more electron. And so now I need it to be the same height as these 2 peaks to indicate that there are 2 electrons. For the next question, you're given the PES data for the 1s sublevel of lithium and the 1s sublevel of sodium, and it says that a student claims that element A is lithium. Do you agree with the claim? Justify your answer in terms of Coulomb's law and atomic structure. So again, there are 2 things that you need to do here. You need to answer the question, do you agree or disagree? And then you need to justify your answer, and you're doing it for Coulomb's law and in terms of the atomic structure. So again, press stop, answer the question, and then press play when you're ready to continue. So in this case, you should not agree with this student. Lithium has 3 protons and sodium has 11. And so according to Coulomb's law, the higher the magnitude of charge, the stronger the force of the attraction. And so since lithium has more protons, the 1s electrons for lithium will be more attracted to the nucleus and will be less attracted to the nucleus and will have lower binding energy. This is the end of the video. Thank you for watching. Please join me for the next video, which will be on trends of the periodic table. This is Mrs. Pudi. Have a great day.